So we left off last time looking at what would happen if we took some sort of a specimen. And I showed you some of these prepared specimens like this, and then some that had already stretched a bit. Put some of these up here. And we'll come back and look at these again for different reasons. But these all started out at about the same length, and you can see that they stretched quite a bit. Okay, the white one there, this one that's in one piece, that's some sort of a plastic or vinyl. This is steel, and the brighter one is aluminum. So what I'd like to look at then is the process of stretching this and the information that we might get from that and what we could do with that. So we take that specimen and we're going to monitor its original length and then also how far it stretches. So oftentimes we'll just take a 2-inch gauge length. If you look at these specimens, they usually have a couple marks on them like that were originally 2 inches apart. And we put some sort of tool on there that would measure how far that 2 inches stretched. So we had the original length, and then we had how much it stretched. So with that, we could calculate the strain, the stretch divided by the original length. And then in the machine that we might put it in, we could monitor the force. We'd probably measure that with some sort of hydraulic pressure. With that force, we could take that force and divide by the cross-sectional area. It's just going to be a round cross-sectional area, although it could be a square specimen. That's possible too. Divide by the cross-sectional area, and we could get then stress. And what we want to do is we want to plot that stress and strain, and we'll come up with a graph here. And I'm going to try and draw this graph fairly large. You may want to follow suit because I'm going to put quite a few comments on it. The graph will usually go up something like this and kind of roll over and then start to go up again. And we'll usually have failure at this point. And then we might have a curve. We'll have to talk about this. Depending on what we look at, maybe we would have failure up there. So let me talk about some of these pieces. This region in here, when it looks linear, is just that, linearly elastic. Okay, linearly elastic. And the linear elastic region, it will, if you take the load off of it, it will return to its original shape. So when we're in the linear region, we apply a load to it. If we take the load off, it goes back to its original shape. You've maybe had this where you're trying to shape a coat hanger into something. You bend it just a tiny little bit, and what's it do? It springs back, right? Okay, so you're in the linear region there. And the value here as far as stress, we say this is the proportional limit. The proportional limit. Okay. Now there's this little rollover here, and as it goes up to here, this is what we call the yield stress. Okay, the yield stress, and it's going to start to deform and never go back at that point. Maybe you've heard about torque to yield fasteners, where you've got a bolt and you actually tighten it till it yields, which then works great, but if you then take it back out to do some maintenance or something, you have to throw the fastener away. It never goes back to its original shape. So it's yielded at that point. And what we call this region up to here, we call this then the elastic region. The elastic region. Incidentally, this linear region, this is all of our class. So this is EGR 213. All of our work's going to be in the linear region. Okay? Those of you who go in mechanical and civil, we'll talk about some of the other regions. But we could include this little rollover here. We could say that that's the elastic region. Anything beyond that is what we call plastic. Okay? Plastic deformation. It's not coming back. That's like a crumple zone in a car. Okay, it'll absorb a tremendous amount of energy, but it's not coming back. So plastic is not necessarily a bad thing. We use plastic design all the time, and eventually you'll talk about that. But we're going to reserve most of this class to the linear region. Okay. What we have happening in here, if I put some more definitions here, we'll talk about this being perfectly plastic. where this line is almost horizontal in the perfectly plastic region. And then at this point, we have what's known as strain hardening. Okay. Take that coat hanger again that you're trying to fashion something into, and you want to break it into two pieces, get it into two pieces. You don't have wire cutters with you. So what do? You bend it back and forth, right? Are you hoping that it gets hot enough and it melts? And it probably does get a little warm, but certainly not hot enough to melt. What are you trying to do by bending it back and forth? Yeah, I mean, you might talk about fatigue. Usually when we talk about fatigue, we're thinking about thousands and millions of cycles. So we might be tempted to think about fatigue, but probably what we're really trying to do is we're trying to work harden it. Maybe you've had a toy or something that has these little metal tabs on it that get bent over when you put it together, and if you want to take it apart, you bend them back. You only bend them over and bend them back so many times, and then they do what? They break off altogether, right? So that's what you're doing with that coat hanger. You're trying to harden that. You're strain hardening it, and once it gets hard enough, then you can just break it like a candy cane or a piece of glass, right? So we are in the strain hardening region there. Beyond this, we have what's known as necking. And the specimens here show that pretty readily. You'll notice that neck down, it started out at a 1/2 inch diameter and neck down. So if you look at the stress value, it actually goes up pretty substantially because you have a very small area now because it's neck down supporting that load. We would say that this region here is at these is failure. So... And the difference is whether we use true strain or engineering strain. And remember that strain is equal to the deformation divided by the original dimension. So if we're using the original cross section, that's the engineering strain. And we have this value. If we use that reduced cross-section, the value is actually even higher. Most of our comments will be reserved to engineering strain. So that's why there's two possibilities there. So these are some things. Like I said, this is where we're going to do most of our work in here, but I wanted to show you that diagram. This would be pretty common for something like something that's ductile. Maybe a mild steel might be a good example of that. Okay, something that's not necessarily that ductile, a piece of brittle, something that's brittle. If we have the stress and the strain, it's probably going to look something like this. It's just going to come up and fail like this. So this would be brittle. Maybe a good example of this is cast iron. Okay. And probably both of these, I have not really done the graph a lot of justice. If I were to draw this more to a scale, if it were to be a more real life here, both of these graphs, the slope of this would be very, very steep. It would come right up here, and then it would start to go over. Okay, so I've exaggerated this a little bit. I've moved this over a little bit so that we could see it. That linear region there is very, very steep. Okay. So it's probably going to look something more like that in real life. Well, let's talk about some of those pieces, some of those definitions. So we talked about the elastic region, or if something was elastic. Okay, elastic returns to the original dimension when the load is removed. And those of you that go into mechanical, go into fasteners and whatnot, this is a big deal, how much you get in terms of your fastener stretch and whether you're going to go into have it yield or not. Then there's the linearly elastic. And this is where stress is proportional. I'll use the symbol proportional to strain. So stress is proportional to strain. So if I go back to this curve, if stress is proportional to strain, I can look at the slope of this. We have sigma here, and we have the strain there, don't we? Okay, so that's going to bring us into Hooke's law. So we can talk about Hooke's law that says that the stress is equal to the modulus of elasticity E times the strain, which is actually the slope of that linear region. Because if I rearrange that, I could say that E is equal to the stress sigma divided by the strain epsilon, right? If I look at units on this, epsilon has no units, so E has the same units as stress. Okay, and this goes by a couple of different names. We could call this the modulus of elasticity. Or we could call it Young's modulus. We will use those terms interchangeably. So if we talk about modulus of elasticity or Young's modulus, and essentially that gives us, well, as you see there, the slope of the linearly elastic region, but it also, in a greater sense, tells us how stiff this is. We would expect the E value for aluminum to be different than steel, for oak to be different than fir, and so forth. I guess if I finish up these definitions here, maybe I should talk about plastic. Say material does not return with load removal. Okay, so like the crumple zone in a car, it's not like some odd sci-fi movie where it uncrumples itself and it stays there. Okay, once you remove the load, it stays there. Civil engineers also do this in buildings. This is something, we don't say buildings are earthquake proof, we say they're earthquake resistant. Hopefully the structures will absorb enough energy that we can get the people out of there. So a lot of times the building may be ruined. It may have gone into the plastic region, but hopefully the occupants have got out of the building. Certainly we see this, and you've seen this in crumple zones in cars and things like that. So yeah, I think we're hopefully pretty good with that. If we look at some common values here, talk about so let's look at some common values for E. We'll say this is in the PSI. Sometimes we'll write it in KSI. And maybe even we'll talk about sigma yield to give us some sense when that yield stress is. And again, I will do that in PSI. And let's look at three very common engineering materials: steel and aluminum and wood. And having said that, you know, what alloy of steel are we talking about? That can vary dramatically, as is aluminum, and even the variety of wood. But just generally, very generally speaking, we could talk about 30 times 10 to the 6. And that's fairly constant for a lot of alloys. Certainly if we look at mild steel or something like that, we would be right in that range, 30 million PSI. If we look at the yield stress, then the yield stress is going to change a lot depending on the alloy. We're going to go from about 30,000 PSI to somewhere probably close to 200,000 PSI. So if we go to like a wrought iron or something like that, they used to make armor out of hundreds of years ago, we might even be 28,000 PSI or something like that. You go down and you buy mild steel. We call it A36 steel. That's because it's 36,000 PSI. You start looking at some more exotic steel, some T1 steel or something, you start getting into the 120, 150 range and things like that. Likewise, aluminum is about a third of this, so we think of the E value, Young's modulus, as 10 million. And again, that's fairly consistent through the alloys. And then usually this range from about 10,000 psi to 100,000 plus psi, depending on the alloy. You can get some pretty sophisticated aluminum alloys. Wood usually hangs out about 1.2 to about 1.7 times 10 to the 6th, okay, depending on the variety of wood and the quality of wood. And the values here go from about 1,000 to about 5,000 psi, depending on the quality of the wood and the variety. So let's give you some rough ideas of some of those values. I guess one of the things to think about is, I always thought about when I was going through school that this was just some experiment that we did while we were in school and whatnot. You put the specimen in there, you pull it apart, you plot your curve, and then it gives you something to talk about, right? I mean, to that point, I think you got a homework problem on this thing. So we'll make this page 3. I think one of your homework problems looks like this. It's a tensile test. So we've got the material is steel, and we're going to start out with a 2-inch length, and it has diameter of about 1/2 inch, so it's a specimen that looks very much like this, okay, when it starts out. And the strain gauge factor, all that means is that we take this number here and we multiply it times that, okay. So what we're going to do is we take the test data, so we got different values of load, and we got different values of strain gauge reading. So what you're going to want to do is, if you want to get strain, you just take this gauge reading here, you would have 1, and then you'd have to multiply that by the factor, 5 times 10 to the minus 5. And here, if you wanted to get stress, what would you do? You take the load, you take that 1,000. Remember, stress is force divided by area, so the load divided by the area, so we're going to have to divide this by, it's a 1/2 inch diameter, so we'd have pi times 1/2 squared over 4. So you could do that for each one of these and have a column of now stress and strain, and you could plot that, right? Okay, and what that would look like then, would look something like this, and I think this is from the homework here. So I started out with my load, and I got my stress from the load, so we get the stress from the load, and then I started out with my strain gauge reading, and I got the strain from that, and then I plotted strain here, and I plotted stress here, and I found the slope of that. It's kind of dark, you can't really see the slope, but the slope of this ends up being E. And so what should the slope be roughly if it's steel? It should be around 30 million, right? Yeah, we'd hope it's around 30 million. Questions with that? So you can do this experiment. We used to have a machine, you had to have it calibrated every year, and then you try and use it once a year. It really was not cost effective, and with all the remodeling and whatnot, they got rid of the machine. But this is actual data, so it gives you a chance to go through and do this. But I wanted to make sure that we didn't get sidetracked in thinking that, well, this was just an academic process, because it's really not. When we used to take tours to the steel mill over in McMinnville, they would they take old barbecues and car bumpers and they turn it into rebar. If you're going to put that rebar in a nuclear plant or something, you probably want to make sure that you have just the right number of car bumpers and barbecues, right, to make it a quality product. So they would test it chemically, but they would also test it mechanically. They'd take a piece of rebar and they would pull it apart. And they would look at the stress-strain curve. And they wanted a stress-strain curve that went up and did something like that. If they got a stress-strain curve that came up and then failed, that was a problem, right? Okay. They actually had a pretty cool machine over there. They could take a number 18 bar, I believe. So let's see, rebar is represented by 8s. So 18 bar would be 2 1/4 inches. So 2 1/4 inch diameter bar and pull it apart. I was actually involved in this when I was at Precision Cast. We made a lot of jet parts and things like that, some kind of cool stuff. And let's say that you have a large compressor casing for a jet engine. Looks something like that. And you cast it, and you've got this hole there. Okay, that's always funny. People say, "Oh yeah, they weld up the holes," and yeah, we'd weld up a hole you could put your fist through. So you get into this part for about $250,000. Okay, so you had $250,000 into that part with a hole in it. So it's probably worth some welding it up. Okay. Well, how do you know your welding process is any good? Well, one, after the welding process, we'd go through heat treat. We'd x-ray it. When I was there, we were the largest purchaser of x-ray film in the world, so we'd x-ray it to make sure that it's sound. But one of the things that we would want to do is we would want to make sure that our process is correct. So we'd take some material that was very much like this, a specimen of it, and I would grind through there. Okay, so you get my eraser here. So I'd grind this out like that, and I'd send it to weld up. We had great welders there, and they would go in and they would use the same process that they proposed to use on this, and they would weld this up. They'd fill it up. It's a TIG process. They'd fill it all up, and they'd send it back to me. Okay, so what did I do? I'd come in and I'd grind this side out. Okay, so I'd grind that side out of it. Okay, and I'd send it to weld up. They loved me at weld up. Okay, so then they'd go in again with the proposed process, and they would weld it up. Okay, and when we got it back, what would we do? Well, we would test it, right? And what would we get to find out? We'd get to find out about those weld properties, and we'd be looking like this. How ductile is the weld? How brittle is the weld? We could figure out if this is going to work or not, right? Yeah. So I don't want you to think that this testing is just something that we do for academic purposes. Not at all. There's people that are in production that are doing these tests all the time. Those of you that go into civil engineering, you'll do a little different test. You'll take a concrete specimen like this, and you'll try and crush it and see how it behaves. That becomes important, right? You're going to put a bunch of concrete into the bridge. You'll have a few samples. You'll have them fill up the samples. You'll cure them, hopefully, so that it reflects how the bridge was cured, and you'll test those. Okay? If you go into a business where you're welding up jet engine parts and whatnot, you'll probably be doing lots of tests like this. So this is not something that's just academic in nature. Questions with those? Questions? Everyone's good? Well, let's continue on then. So we talked about stress and strain. Another one that we need to talk about is Poisson's ratio. So lots of cool names. Poisson's ratio. So Poisson's ratio, by definition, we use the symbol nu, N-U, pronounced N-E-W. Okay, so lots of Greek symbols in here. I think on my website I have a Greek symbol key. If you can't find it under this class, go and look at it under like GE 101. So we've got nu, Poisson's ratio, is given as minus the lateral strain divided by the axial strain. Remember when last time we were talking about that axial strain, how it got longer, and we said that the lateral strain, it did something there. We were going to say that, well, it was non-zero and just leave it as that. Well, with Poisson's ratio, we can start talking about that more. We can relate the lateral strain to the axial strain. We do that with Poisson's ratio. It's a material constant. And in most materials, it's pretty close to 0.3. Okay, so pretty close to that number, but that's something that you could look up. So let's try an example then. Put this all together and say that we have a specimen here we'll say that it's 3 inches long and 2 inches in diameter. There's a symbol for diameter. And we put an unknown compressive load on it. Okay, so we put an unknown compressive load on it. We know that the thing is aluminum, and therefore because it's aluminum we could look up, we would take E as 10 times 10 to the 6 psi, Young's modulus or modulus of elasticity, and Poisson's ratio we could look up as 0.3. Okay, when it's loaded, put an unknown compressive load on it, and it shortens. Shortens by 0.012 inches. Okay, 12 thousandths of an inch, it gets shorter. So what we'd like to do is we would like to then find the change in diameter and axial stress. Okay, so what equations do we have? Well, we've got what? Stress, we know, is force divided by area. Strain, we know, is change in dimension divided by original dimension, or change in length divided by original length. And of course, we have just learned about Poisson's ratio. That Poisson's ratio minus the lateral strain over the axial strain. I guess one last thing is we have Hooke's law now that relates these two, doesn't it? What do we say with Hooke's law? That stress sigma is equal to Young's modulus E times the strain epsilon. So I'll spend a lot of time writing these out because they are deceptively simple equations, only 3 variables in each equation, and I think we really want to have those in front of us as we try and do this. So let's see, what do we know about in the axial direction? In the axial direction, do we know what's going on there? Let's see, it shortens how much? 12 thousandths of an inch. So if I take that 0.012 inches, and I'll put a negative because it gets shorter, and I'm going to divide this by the original length. The original length was 3 inches. I get to cancel the inches, and I get a number that is minus 4 times 10 to the minus 3. And what's that? What could we call that? We could actually call that epsilon x. If I take x in the axial direction and y in the lateral direction, I could say that's epsilon x. That is our axial strain, isn't it? Well, let's see. I could use Poisson's ratio then to get my lateral strain, couldn't I? So I could say that with Poisson's ratio, which is equal to 0.3 for this material, that's equal to minus epsilon y divided by epsilon x. Well, we know epsilon x, so we have minus epsilon y divided by epsilon x, which is minus 4 times 10 to the minus 3. So with this, I'm able to calculate or get epsilon y. Epsilon y turns out to be 1.2 times 10 to the minus 3. Well, it's positive. So we could say that this would really be equal to the change in the diameter divided by the original diameter. And just like we talk about change in length divided by the original length. And if we're compressing this and it's getting shorter, what would we expect the diameter to do? To get larger, wouldn't we? So it should make sense that this is indeed a positive number. So if we go through this, we could set this equal to change in diameter divided by the original diameter, which is 2 inches. And we could solve for that. And do I have a number there? Yeah, 0.0024. Okay. So the diameter gets larger by 0.0024, 24 ten thousandths of an inch. which could be a problem if we're trying to push this out of something. I mean, if this is a pin that's stuck in something and we're trying to push it out, as we try and press that out and put that axial load on it, it's kind of a double-edged sword. It gets bigger, doesn't it? Okay? So that's how much larger the diameter gets. So we got change in diameter. How about axial stress? Do we have that? This is such a great building. So, I was checking out, I used to not be allergic to pollen at all, but now if you run your fingers along the window, well, if you're allergic to pollen, don't do this. So, anyway, so I've gone off on a tangent here, so I apologize to people watching on the video in years to come. But anyway, so let's see. We want the axial stress. We've been talking a lot about strain. How can I get from strain back to stress? Well, I use Hooke's law will get me from strain to stress. Let's see if I can do that. I could say that sigma x is equal to Young's modulus times epsilon x, right? Do I know Young's modulus? Yeah. 10 times 10 to the 6th psi. Do I have epsilon x? Yeah, right there. Minus 4 times 10 to the minus 3 doesn't have any units. So this turns out to be equal to minus 40,000 psi. Again, our strain numbers were typically small numbers, 10 to the minus 3, 10 to the minus 4. We're unitless. Our stress numbers are large numbers, thousands. And they have units of psi, so I think this works. This negative sign, does that concern you? No, I think we're okay, because we would expect this to be in what kind of stress? Yeah, compression. So it should have a negative sign. Questions with that? No questions? So, like I said, these equations are deceptively simple. They are small equations, but oftentimes it can be very handy to have them in front of you, to write them out and look at how we can use those. Questions with that? Well, the next thing I want to go to is I want to talk about shear stress. Okay, shear stress. And shear stress is pretty easy. We give it the symbol tau, and tau is equal to force divided by area. The work is always, well, what's the force and what's the area? And I brought a little example here. I brought my Timoshenko book. It says Gear, but don't pay any attention to that. When Timoshenko died, Gear took it over, and Gear died recently, and someone else took it over and kind of messed up the whole book. I refer back to Timoshenko because I'll show you a picture here, and I realize that the picture is probably kind of hard to see, but go Google a picture of Timoshenko. He was a Russian immigrant to the United States at about the time of Igor Sikorsky and things like that with the Russian Revolution, and was really the father of this subject. So he wrote lots of books in different languages and whatnot. So a lot of times I'll refer to Timoshenko, and if you get a chance to buy one of his books, I would encourage you to do so. But I'm going to use Timoshenko's book in a little different way today. I'm going to put my Post-it note on it here. I like these Post-it notes. They were developed by 3M, right? So that's your question, is to figure out what 3M stands for. So if I take this Post-it note, it's not very strong if I pull it off in this direction, right? Okay, the adhesive is not very good in tension. Wouldn't you agree that that's tension? Comes right off in tension. But if I stick it on like this and I pull it like this, the adhesive is acting in what fashion? It's in shear, and adhesive is really good. Glues are really good in shear. Okay, so what kind of a area are we looking at there? Well, we're looking at something that looks like this. Well, they just developed the Post-it note. I'm not trying to get you to buy stock in 3M, but that's just, yeah. What? Yes?
I actually read that the Post-it note became an accident. They were actually trying to create super glue.
That could be.
And they kind of backfired, and they instead developed something really weak that they found.
Yeah. A very lucrative use for. Yeah, tremendously lucrative. Well, and speaking of super glue, what was it developed for? Astronauts? No? A little more. Like what? Yeah, it was during the Vietnam War, massive battlefield traumas to glue yourself back together. So yeah. So if we look at this, we look at that interaction of the Post-it note and the textbook. We might have some force here and some force here, so we could say that this was F and that was F. And the area that this acts over looks something like this. I think this is easier to draw on the board. But anyway, the area that this acts over, where that adhesive might be or where they're stuck together, looks something like this. So this is our area. Okay, and that's our force. And we could represent across that area, we could represent this shear stress. So this would be an equilibrium. This shear stress would be tau. So again, it's just a matter of figuring out what the force is and what area that acts over. If we look at the equation here, tau, the shear stress, is equal to force divided by area. What kind of units does it have? Yeah, it's going to be a PSI or KSI or pascals, most likely megapascals or gigapascals, the same as normal stress. And a lot of times we'll talk about this as the average shear stress because we don't want to get too close to the edges or a discontinuity or a hole or something like that. So maybe we'd say this is the average shear stress. Okay, the average shear stress. And what I want to do is I want to go down and I want to look at an element right on the surface there. And the element might look something like this. I'll talk about this as a stress element. And if I represent the shear stresses on the stress element, they will look something like this. Okay, these are going to be shear stresses. So I could say that that would be tau. Incidentally, if I wanted to put normal stresses on that stress element, I could do it like this. That would be sigma, and I could have them in both directions. But I'll just keep it simple here, and I'll leave that tau there. Well, if you look at how this is going to deform, because I want to talk about the shear deformation, if I take this thing and I put these stresses on it like this, how do you think it's going to deform? Do you think that it might look something like this, like a box that's all racked over? You buy that? Okay. And if we measure this, we're going to talk about this angle in here. And I'm going to say that angle is gamma. And we're going to define gamma as the shear strain. So gamma is defined as the shear strain. It's defined as the shear strain, and it's in radians. Okay? So it's essentially unitless then. So we've talked about the shear stress, tau. We've talked about the shear strain, that's gamma. Do you think we can relate these? Oh, absolutely. We have a Hooke's law for shear. Okay, and Hooke's law for shear says that the shear stress tau is equal to the shear modulus elasticity G times the shear strain gamma. So G is the shear modulus elasticity. Okay, G is the shear modulus elasticity. Since gamma is in radians, G would have to have the same units as tau, right? So it's going to have PSI or KSI or pascals or something like that. Now you might wonder, well, I know what G is named. What in the world is G? Well, we'll actually find later on in a few weeks, we will actually be able to derive this when we talk about torsional work. But G is actually equal to Young's modulus E divided by 2 times the quantity 1 plus Poisson's ratio. Okay. So we actually have start to have lots of equations, don't we? I mean, if I sum up our work today, I'll leave this here so you can write it down. But what equations have we looked at? We've got normal stress as equal to force divided by area. I have normal strain epsilon is equal to delta over L. I relate those with Hooke's law, that sigma is equal to Young's modulus times the strain epsilon. I have Poisson's ratio, where minus epsilon lateral over epsilon axial. What else do we have? We have tau is equal to force divided by area. We had that tau is also equal to, by Hooke's law for shear, G, the shear modulus of elasticity times gamma. Better talk about G. G we saw, and we will derive eventually, but for now I'll just leave it like this. E divided by 2 times 1 plus Poisson's ratio. So when you sit down to do homework problems or study, I would encourage you to list these out. That will help you doing the problems. It will also help you get used to remembering these equations, because like I say, they're very simple equations, but you want to have them in front of you to help you get through the problems. We have lots more simple equations to add to this in the future. So when we get together next time, we'll have that quiz like we're talking about and continue on with this study. Take care till then.